Hello everybody, this is the ninth day of our crash course, and we're going to learn some advanced tuning techniques, namely hyperparameter tuning, knowledge distillation, model quantization and pruning, parallel and distributed training. For more AI courses and interview materials, please go to bowsy8.com. Hyperparameter tuning is crucial for optimizing large language models, LLMs. Unlike model parameters, hyperparameters are manually set and impact training stability, efficiency, and accuracy. Important hyperparameters include learning rate, which affects weight updates, and batch size, which influences training dynamics. Weight decay helps prevent overfitting by regularizing the model. Tuning strategies vary. Grid search exhaustively tests all possible values but is expensive. Random search selects hyperparameters randomly and is often faster. Bayesian optimization builds probabilistic models to refine hyperparameter selection efficiently. Effective hyperparameter tuning enhances accuracy, reduces overfitting, and optimizes resource usage, ensuring LLMs perform well across tasks. The learning rate is one of the most critical hyperparameters in LLM tuning. It determines how much model weights are adjusted during each training step. Setting the wrong learning rate can lead to poor convergence, slow training, or unstable updates. A high learning rate makes large updates, which may cause the model to overshoot the optimal solution or diverge. A low learning rate results in slow progress and can trap the model in suboptimal local minima. To optimize learning rates, techniques like learning rate schedules, exponential decay, cosine annealing gradually reduce the rate during training. Warm-up strategies start with a small learning rate, allowing stable early training. Adaptive optimizers like Atom, RMSprop, and Adigrad adjust the learning rate dynamically. Selecting an appropriate learning rate requires experimentation and monitoring of loss curves. Poor tuning can lead to longer training times or suboptimal performance. In the next slides, we'll explore batch size and weight decay, which interact closely with learning rate tuning. Batch size is a key hyperparameter that influences training speed, memory usage, and model generalization. It defines how many training samples are processed before updating model weights. Using a small batch size introduces more stochasticity, meaning more variation in gradient updates. This can help models generalize better but may slow convergence. Conversely, large batch sizes lead to smoother gradient updates, while speeding up training but potentially causing overfitting or poor generalization. The choice of batch size also depends on hardware constraints. Larger batches require more GPU-TPU memory, which may not be feasible for extremely large LLMs. Optimizer choice matters too. For example, Atom is more stable with small batches, while SGD benefits from larger ones. Optimizing batch size involves balancing training efficiency and model generalization. Some methods, like progressive batching, gradually increase batch size to stabilize training. The next slide will cover weight decay, another crucial hyperparameter that interacts with batch size and learning rate. Weight decay is a regularization technique that prevents overfitting by penalizing large weight values. It works by adding an L2 regularization term to the loss function, encouraging the model to maintain smaller weights, which enhances generalization. A higher weight decay forces weights to remain small, reducing overfitting, but potentially leading to underfitting if set too high. On the other hand, low or no weight decay allows more flexibility in learning, but may result in overfitting, especially in large models trained on small or noisy datasets. Weight decay is commonly used with optimizers like Atom W, which decouples weight decay from gradient updates for better performance. The ideal weight decay value depends on dataset complexity, model size, and training duration. Proper tuning of weight decay is essential for achieving better generalization while maintaining training efficiency. Next, we'll explore gradient clipping, another technique for stabilizing model training. Gradient clipping is a technique used to stabilize training by preventing exploding gradients, which can cause weight updates to become too large, leading to instability and divergence. This is particularly important for deep LLM architectures and high learning rate settings. There are two main types of clipping: norm-based clipping rescales gradients if their L2 norm exceeds a threshold. Value clipping directly limits gradients to a fixed maximum value. Norm-based clipping is more common in optimizers like Atom and SGD, as it maintains gradient direction while controlling magnitude. It's especially useful for transformer models where large updates can disrupt learning. Choosing an appropriate clipping threshold is crucial. Too high, and it has little effect. Too low, and training slows down unnecessarily. Proper use of gradient clipping helps improve convergence and training stability, particularly when fine-tuning LLMs. Early stopping is a regularization method that halts training when the validation loss ceases to improve over a specified number of steps, preventing the model from overfitting to the training data. The core idea is to monitor performance on the validation set and stop when the model's generalization ability starts to degrade. Training continues as long as the validation loss improves, but it's stopped when the improvement plateaus, thus avoiding overtraining. This technique is often used alongside cross-validation, which ensures the model is not just memorizing the training data, but can generalize to unseen data. The challenge lies in finding the right balance. Stopping too early may prevent the model from reaching its full potential, while waiting too long may lead to overfitting. Careful tuning of patience, number of epochs without improvement before stopping, and validation set size is important to maximize the benefits of early stopping. In the next slide, we will look into the use of learning rate schedules in hyperparameter tuning. A learning rate schedule modifies the learning rate dynamically during training to improve convergence and prevent the model from getting stuck in local minima. Keeping a constant learning rate throughout training is often suboptimal, as different phases of training benefit from different step sizes. There are multiple scheduling techniques. Step decay reduces the learning rate at fixed intervals. Exponential decay decreases the learning rate exponentially over time. Cosine annealing smoothly reduces the learning rate following a cosine function, often used in transformer-based models. Another effective approach is learning rate warm-up, which starts training with a small learning rate and gradually increases it, helping stabilize early training phases. This is especially useful for very large models like LLMs, where abrupt high learning rates can cause unstable gradients. Optimizers determine how model weights are updated based on gradients. Selecting the right optimizer is crucial for efficient and stable training. SGD, stochastic gradient descent, is simple and effective but requires careful learning rate tuning. ADAM, adaptive moment estimation, is commonly used for LLMs as it dynamically adjusts learning rates per parameter, improving stability. RMS-SPROP and ADAGRAD are useful for handling sparse data and adaptive learning rates. For LLMs, ADAM and its variants ADAM-W, LAM, are preferred due to their ability to handle large-scale training with minimal manual tuning. The optimizer should be chosen based on model architecture, dataset size, and computational constraints. Momentum-based methods improve training by accelerating updates in the right direction, reducing oscillations in gradient descent. This is especially useful for deep networks and noisy gradients. Adaptive gradient methods like ADAGRAD, RMS-SPROP, and ADAM adjust the learning rate individually for each parameter, making training more stable and reducing the need for manual tuning. ADAM combines both momentum and adaptive gradients, making it the preferred optimizer for LLMs. Balancing momentum with adaptive methods improves convergence speed and stability, especially in large-scale models. The next slide will discuss hyperparameter tuning strategies that optimize these settings. Hyperparameter tuning is essential but can be computationally expensive. Manual tuning is inefficient, leading to suboptimal settings. Grid search systematically tests combinations but is computationally heavy. Random search samples from a distribution, often finding good settings faster. Bayesian optimization builds a probabilistic model to intelligently select the next hyperparameter set, reducing search time. For LLMs, efficient tuning strategies are critical to balancing performance and cost. In the next slides, we'll explore advanced search techniques and automation tools. Beyond basic search strategies, advanced techniques improve hyperparameter tuning by making it more adaptive and efficient. Population-based training, PBT, continuously adjusts hyperparameters during training, evolving the best configurations over time. It helps LLMs dynamically adapt learning rates, batch sizes, and weight decay. Hyperband improves random search by efficiently allocating computation to promising configurations while eliminating poor candidates early. It reduces wasted computation and speeds up hyperparameter search. Neural architecture search, NAS, automates both model structure and hyperparameter tuning using reinforcement learning or evolutionary algorithms. This is useful for optimizing LM architectures for specific tasks. Combining these methods, such as Bayesian optimization with PBT, can accelerate training and enhance performance, making them valuable for large-scale AI applications. Batch size is a crucial hyperparameter that affects training stability, speed, and model generalization. Smaller batches provide stochastic noise, which can act as implicit regularization, improving generalization, but making training noisier. Larger batches result in more stable gradients, enabling faster convergence, but sometimes leading to sharper, less generalizable minima. Adaptive strategies such as dynamic batch sizing adjust batch size based on gradient variance, balancing stability and efficiency. For LLMs, choosing the right batch size also depends on memory constraints, as larger batches require more GPU-TPU memory. The next slide will explore weight initialization strategies and their role in training efficiency. Weight initialization significantly affects how quickly and effectively a model learns. Poorly initialized weights can lead to vanishing or exploding gradients, making training unstable. Xavier Glorot initialization is designed for sigmoid and tan activations, ensuring balanced gradient flow in shallow networks. Chiming E initialization is optimized for ReLU-based networks, preventing signal degradation in deep architectures. For LLMs, starting with pre-trained weights from prior models speeds up training and stabilizes learning. Careful initialization helps avoid convergence issues and improves training efficiency. Next, we'll cover gradient accumulation, a technique for handling large models with limited memory. Gradient accumulation allows training large models on limited GPU memory by breaking a large batch into smaller microbatches. Instead of updating weights after every small batch, gradients are stored and accumulated over multiple steps before applying an update. This method enables models to simulate large batch sizes without needing excessive GPU memory, preserving the stability and generalization benefits of large batch training. It's especially useful for LLMs and transformer-based architectures where standard large batch training is memory intensive. In the next slide, we'll discuss optimizing training with mixed precision techniques. Mixed precision training speeds up LLM training by using lower precision FP16 arithmetic where possible, while keeping higher precision FP32 calculations where necessary. This significantly reduces memory consumption and allows training larger models on the same hardware. Key benefits include faster computation. FP16 operations run twice as fast on modern accelerators. Lower memory requirements. More parameters fit into GPU memory. Numerical stability maintains full precision gradients to prevent underflow. Mixed precision is widely adopted in LLM training frameworks like PyTorch and TensorFlow, often paired with automatic loss scaling to prevent instability. Next, we'll transition into knowledge distillation, a technique for compressing large models. Knowledge distillation is a model compression technique that allows a smaller student model to learn from a larger teacher model, reducing computational requirements while maintaining strong performance. One core idea is using soft labels instead of traditional hard labels. The teacher model generates probabilistic outputs, which provide richer information about relationships between classes. This guides the student model to learn more nuanced patterns. Another approach is feature-based distillation, where the student model mimics intermediate layer activations from the teacher. This is useful for LLMs, vision models, and speech recognition, where deeper representations improve model efficiency. Distillation is widely used for deploying LLMs on edge devices or reducing inference latency in production settings. The next slide will explore different types of knowledge distillation. Here are multiple approaches to knowledge distillation, each targeting different aspects of the learning process. Logic-based distillation is the most common, where the teacher model's soft probability outputs guide the student. Instead of learning from hard labels, the student mimics the distribution of predictions, allowing it to learn latent relationships between outputs. Feature-based distillation goes deeper by aligning intermediate feature representations of both models. The student is trained to match hidden layer activations of the teacher, improving knowledge transfer. Attention transfer is particularly useful for transformer-based LLMs. The student learns to replicate attention distributions, improving efficiency without sacrificing comprehension. Response-based distillation focuses on the final output layer, ensuring that the student's predictions closely resemble those of the teacher. Each method has trade-offs, and hybrid approaches are often used to maximize efficiency. Knowledge distillation is essential for deploying LLMs efficiently, as these models are often computationally expensive. A distilled model retains much of the knowledge from a large teacher model while requiring significantly fewer resources. One major benefit is faster inference speed, which is crucial for real-time applications like chatbots, code generation, and search engines. Since smaller models require less memory and computation, they are ideal for mobile and edge devices where full-scale LLMs are impractical. Distillation is also valuable in low-resource environments where training from scratch is not feasible. By leveraging a pre-trained teacher model, organizations can fine-tune a student model more efficiently. This is especially useful in domains with limited computing infrastructure, such as healthcare and IoT. When distilling a large model into a smaller one, there's a clear trade-off between model size and performance. Smaller models are more efficient, requiring less memory and computational power, which allows them to run on edge devices and in real-time environments. However, they may suffer from lower accuracy compared to their larger counterparts, as they cannot capture the full complexity of the task. On the other hand, larger models like the original teacher model typically offer higher accuracy and performance. Yet, they require significantly more resources for both training and inference, which can be prohibitive in many scenarios. Distilled models aim to achieve a middle ground. They retain a substantial portion of the teacher model's accuracy while significantly reducing the size. Fine-tuning these models on task-specific data helps improve their performance and adapt them for real-world applications, even with fewer parameters. Temperature scaling is a technique used in logit-based distillation to smooth the teacher model's probability outputs. By increasing the temperature during the softmax operation, we reduce the sharpness of the logits, making them more informative for the student model. This helps the student learn the relative likelihoods between classes, rather than just focusing on the most probable output. Higher temperatures produce softer distributions, offering the student model more nuanced gradients. This leads to improved learning of the underlying patterns as the student model is guided by a broader set of possibilities rather than a hard prediction. Temperature scaling is particularly useful in highly complex models like LLMs, where the full distribution of outputs contains more valuable information for training. The next slide will discuss challenges in distillation for large-scale models. Distilling large-scale models such as LLMs comes with significant challenges. One primary issue is the sheer computational resources required for distillation. Not only does the teacher model need to be trained, but the distillation process itself requires additional computational power to create and fine-tune the student model. This is especially challenging in environments with limited hardware resources. A major difficulty is maintaining accuracy in the distilled model. As we reduce the size of the student model, it often cannot capture all the intricate features of the teacher model, which can lead to performance degradation. The disparity between teacher and student can cause the student model to struggle in replicating the teacher's understanding of the task. In addition, the process faces memory and computational bottlenecks, especially when training at scale. Techniques like gradient accumulation or mixed precision can help, but still require careful management of resources. Despite these challenges, the trade-off between model efficiency and performance makes distillation a powerful tool in real-world applications. To achieve efficient knowledge distillation for LLMs, it's essential to begin with pre-trained models as teachers. These models have already learned from vast data sets, allowing the student model to benefit from this prior knowledge, speeding up the convergence time during training. Gradually reduce the student model's complexity, starting with a larger student and progressively pruning it. This allows the student to learn progressively simplified representations from the teacher without overwhelming it from the start. This gradual approach can help achieve better results compared to immediately training a small student model. In addition, applying feature distillation rather than relying solely on logit-based methods allows for more precise representation transfer. This helps the student model learn important features and hidden patterns that would be difficult to capture using just output probabilities. Finally, optimizing the training schedule for the distillation task is crucial. Fine-tuning the learning rate, batch size, and gradient accumulation steps can greatly impact the success of distillation, especially for large models like LLMs. When training a student model through knowledge distillation, the loss function is key to ensuring that the student model mimics the teacher model effectively. The distillation loss typically combines cross-entropy loss, which compares predicted labels to true labels, with KL divergence, which compares the teacher's probability distribution with the student's. The cross-entropy loss focuses on the final predictions, ensuring that the student model's predictions align with the true labels. Meanwhile, KL divergence measures the difference in the soft outputs between the teacher and student, encouraging the student model to learn the teacher's nuanced decision-making. By balancing these two losses, we ensure that the student both accurately predicts the true labels and effectively learns from the teacher's probabilistic knowledge. This approach is vital for LLMs, where the knowledge transfer from the teacher's deep learning is essential for efficient model performance. In knowledge distillation, soft labels are a crucial element. Instead of using traditional hard labels, which are one-hot encoded and only indicate the correct class, we use soft labels, which are the probability distributions output by the teacher model. These soft labels provide much richer information about the likelihood of each class and the relationships between them. This richer information helps the student model learn not just the correct class, but also the uncertainty in the teacher's decision. For instance, if the teacher model is unsure between two classes, the student can learn to reflect this uncertainty in its own predictions. Using hard labels can sometimes result in overfitting, especially in smaller student models. Since hard labels provide only binary classification information, correct or not, the model may focus too narrowly on perfect accuracy without understanding broader patterns. In knowledge distillation, temperature scaling plays a pivotal role in shaping the teacher model's output. The temperature parameter controls the sharpness of the softmax distribution produced by the teacher model. When the temperature is high, the output distribution becomes softer, meaning the probability mass is more evenly distributed across different classes. This allows the student model to learn richer information, as the teacher model reveals not just the most likely class, but also the uncertainty between classes. Conversely, a low temperature results in a sharper distribution, where the teacher's predictions are more confident and focused on the most probable class. This is useful for emphasizing the most probable outcomes, but it can reduce the richness of the learned knowledge. Overall, adjusting the temperature during distillation helps control the trade-off between knowledge transfer and accuracy. Data augmentation is a valuable technique in knowledge distillation because it helps improve generalization for both the teacher and the student models. By artificially expanding the training dataset with various transformations like rotation, scaling, or adding noise, we expose the models to a wider variety of examples, making them more robust. For LLMs, data augmentation techniques like back translation or word substitution are commonly used to create new examples. For image-based tasks, transformations can include flipping, cropping, or changing colors, which help the model generalize better across diverse input data. Augmented data helps ensure that the student model doesn't just memorize the training data, but also learns robust features that generalize well to new unseen inputs. This is particularly important for distilling knowledge from a large teacher model that has seen a wide range of data. One of the challenges in knowledge distillation is the teacher-student disparity. The teacher model is typically much larger and more powerful, capable of learning complex patterns and representations. However, the student model is smaller and has limited capacity, which can make it difficult to fully replicate the teacher's expertise. This gap often results in the student model not achieving the same performance as the teacher, even when it has been trained on the same data. To mitigate this, fine-tuning the student model on task-specific data can help it better capture the teacher's knowledge. Additionally, careful architecture design is necessary to ensure that the student model can at least partially mimic the teacher's reasoning process, even if it cannot exactly replicate all of the teacher's capacity. A hybrid approach to knowledge distillation combines multiple distillation methods, such as logit-based and feature-based techniques. This allows the student to learn from both the output probabilities of the teacher, logits, and the internal representations, features of the teacher model, which together offer a more comprehensive knowledge transfer. This hybrid strategy helps balance the advantages of both techniques. Logit-based distillation ensures the student is aligned with the teacher's predictions, while feature-based distillation improves the learning of more abstract representations. Another interesting approach is multi-teacher distillation, where knowledge is transferred from multiple teacher models. By combining knowledge from different teacher models, the student can potentially learn from a broader spectrum of behaviors and perform better across diverse tasks. While knowledge distillation is a powerful technique, it comes with its own set of challenges. The use of hybrid and multi-teacher models often increases the complexity of the training process. Balancing the contributions from multiple teachers or incorporating both logits and features requires careful tuning to avoid overfitting the student model to the teacher's knowledge. Moreover, the quality of data used for distillation plays a significant role in performance. If the teacher model was trained on high quality data, the student model may struggle to generalize on low quality or unstructured data, reducing the effectiveness of the distillation. Regularization methods can help, but without diverse and accurate training data, knowledge transfer may not be fully successful. Additionally, transfer learning between domains or tasks can present limitations. For instance, knowledge distilled from a teacher trained on one domain may not be directly applicable to another domain with very different characteristics. Knowledge distillation has significant real-world applications, especially in scenarios where deployment on edge devices or resource-constrained environments is required. In these settings, the student model, which is smaller, faster, and more efficient, can maintain high performance while consuming fewer resources, making it ideal for mobile applications and IoT devices. In natural language processing, NLP, and computer vision, distilled models enable faster processing times for real-time applications like speech recognition, automated translation, and image classification. These applications benefit from the efficiency of distilled models, which can operate with limited computational power while maintaining much of the performance of the larger teacher models. Moreover, knowledge distillation is an essential technique for scaling AI applications, where large models need to be deployed across a wide range of devices with varying capabilities. The ability to create efficient and high-performing models that can run on everything from smartphones to cloud servers is vital for enabling AI at scale. Model quantization is a technique used to reduce the size of a model and enhance its computational efficiency. The core idea is to reduce the precision of the model weights, converting them from floating point numbers, usually 32-bit, to integer values, such as 8-bit. This process reduces the memory footprint, making models more efficient to store and execute. The main advantage of quantization is the substantial reduction in the model size, which is particularly useful for deploying deep learning models on embedded systems, mobile devices, and edge devices, where memory and computational resources are limited. This leads to faster inference and improved power efficiency, which is critical for real-time AI applications. While the process is beneficial in terms of efficiency, it comes with the challenge of potentially reducing the model's accuracy, which must be managed carefully during the tuning phase. There are several types of quantization approaches, each suited to different scenarios. Post-training quantization is applied after the model has been trained. This approach is the simplest and most commonly used, where the pre-trained model's weights and activations are quantized to lower precision. Quantization-aware training, key, integrates quantization directly into the training process. During Q8, the model is trained while simulating quantization, allowing the model to adapt and minimize accuracy loss when the weights are eventually quantized. This approach often leads to better accuracy retention compared to post-training quantization. There are also uniform and non-uniform quantization techniques. In uniform quantization, the range of values is divided evenly, while in non-uniform quantization, different ranges of values can have different precision, often based on the distribution of weights. Dynamic quantization applies varying levels of precision at inference time, adjusting depending on the computation needs or model layers. Quantization offers several compelling benefits, especially for deploying models in resource-constrained environments. One of the key advantages is the reduction in model size. By lowering the precision of weights and activations, the model's storage requirements decrease significantly, making it easier to deploy models to edge devices, mobile phones, or IoT devices. Additionally, inference speed is greatly enhanced as integer operations are computationally cheaper than floating point operations, leading to faster real-time processing. This is essential for applications like speech recognition, image classification, and autonomous driving, where fast decision-making is crucial. Quantization also allows models to run with lower memory usage, which is important when dealing with large models that would otherwise consume excessive amounts of memory on smaller devices. The main challenge of quantization is balancing the trade-off between efficiency and accuracy, but with the right tuning, minimal accuracy loss can be achieved. While model quantization offers notable benefits, it also presents some challenges. One of the most significant drawbacks is accuracy loss. As model weights are reduced from floating point precision to integers, fine details of the learned model may be lost, potentially leading to decreased performance. This is especially problematic when quantizing large models with many parameters. Another challenge is that hardware support for quantization techniques can vary, and some devices may not support advanced quantization methods like non-uniform quantization or quantization-aware training. Ensuring that the hardware supports the chosen quantization scheme is essential for deployment. Additionally, the fine-tuning process required to optimize the quantized model can be complex and time-consuming. Proper regularization techniques need to be applied to avoid overfitting during this phase. Finally, not all model architectures are well suited to quantization. Models with high sensitivity to weight precision, such as transformers and RNNs, may face larger challenges during this process. Model pruning is a technique used to reduce the size and complexity of deep learning models by removing weights or neurons that are deemed unnecessary or unimportant. Pruning is often used in conjunction with other techniques like quantization to further optimize a model for deployment. The main idea behind pruning is that not all weights in a neural network are equally important. By identifying and removing less important weights based on their magnitude or impact on loss, we can reduce the model size and make it more efficient. Additionally, pruning leads to sparsity, which means that many of the model's weights are zero, potentially improving computational efficiency during inference. Furthermore, pruning can also reduce overfitting, as removing unnecessary weights prevents the model from becoming overly complex and overfitting to the training data. There are several types of pruning methods, each with different strategies for reducing model size and complexity. Weight pruning involves removing individual weights between neurons. This method can result in significant sparsity in the model and is often used for fully connected layers in deep neural networks. Neuron pruning removes entire neurons or filters from convolutional layers. This technique is especially useful for pruning deep convolutional neural networks, CNNs, as it can lead to both reduced complexity and improved computation efficiency. Structured pruning is more aggressive, as it removes entire layers or blocks of the model. This method is typically used for transformer models or models that require more significant reductions in their architecture. Unstructured pruning removes individual weights regardless of their position, which can result in sparse matrices. This method is flexible but may not take advantage of hardware optimizations. When choosing a pruning strategy, we have two common approaches: magnitude-based pruning and gradient-based pruning. Magnitude-based pruning is the most straightforward and involves removing weights whose absolute values are smallest. The rationale is that smaller weights contribute less to the model's overall output. This method is computationally cheap and doesn't require any additional information during training, but it can be less adaptive since it doesn't take into account the role of weights in the network's learning process. Gradient-based pruning, on the other hand, uses the gradient of the loss with respect to each weight to determine its importance. Weights that have a smaller gradient, i.e., contribute less to the loss, are pruned first. This method is more adaptive and can potentially preserve accuracy better, but it requires additional computation during training to calculate gradients for all weights. Pruning brings several significant benefits for model efficiency and deployment. By removing unimportant weights and neurons, pruning effectively reduces the model size, making it easier to store and deploy. This reduction in size also leads to lower memory requirements, which is particularly useful for deploying models on resource-constrained devices like smartphones, embedded systems, or IoT devices. In addition to size reduction, pruning can also speed up inference times. Fewer weights mean fewer calculations are needed during forward propagation, which accelerates real-time processing in applications such as speech recognition or autonomous driving. Finally, pruning can help mitigate the risk of overfitting, as eliminating unnecessary model complexity forces the model to focus on the most important features, making it more generalizable to new data. Pruning techniques can be categorized into two main types: unstructured pruning and structured pruning. Unstructured pruning focuses on removing individual weights that are deemed unimportant based on criteria such as magnitude or gradient. This approach leads to sparse models where many weights are zero, but the overall network architecture remains intact. While it offers flexibility, it often leads to inefficiencies in hardware, as sparsity may not be well optimized on typical processors. Structured pruning is more aggressive and involves removing entire neurons, filters, or even layers. This type of pruning creates a more compact model by reducing the dimensionality of the network. It is often more suitable for hardware optimizations like parallel processing, as it eliminates entire components rather than just individual weights. Both methods have their place depending on the target deployment platform and the desired trade-offs between model efficiency and complexity. Combining model quantization and pruning allows us to achieve synergistic effects, resulting in even more efficient models. The idea behind this approach is that pruning removes unnecessary weights, significantly reducing the model size and complexity. Once pruning is complete, quantization can further reduce the model's size by lowering the precision of the remaining weights. Using pruning to simplify the model structure before applying quantization allows for a more efficient reduction in size and improved performance. While pruning reduces the model's complexity, quantization reduces the memory footprint and accelerates inference by using lower precision weights. This combined approach ensures that we extract the maximum possible efficiency from both techniques, which is crucial when deploying models to edge devices or cloud-based applications. There are two main approaches to pruning based on when and how the pruning rate is adjusted: dynamic pruning and static pruning. Dynamic pruning adjusts the pruning rate during the training process based on the model's performance and behavior. The pruning rate can increase over time as the model converges, allowing for more aggressive pruning once the model has learned the essential patterns in the data. This approach is more adaptive, as it continuously tunes the pruning process in response to the model's training state. Static pruning, on the other hand, applies a fixed pruning rate throughout the training process. This method is simpler and easier to implement, but lacks the flexibility and adaptability of dynamic pruning. It may lead to suboptimal results if the pruning rate doesn't align well with the model's learning dynamics. Model quantization and pruning have a wide range of applications, especially in areas where model efficiency is critical. These techniques are used extensively in natural language processing (NLP) tasks, where large pre-trained models can be quantized and pruned for deployment on mobile or edge devices. In computer vision, real-time object detection and image classification can be greatly enhanced by using smaller, pruned models that are quantized for faster processing. In the context of edge devices and IoT, both techniques are essential for deploying AI models to resource-constrained devices with limited computational power. AI-powered robotics also benefits from these methods, enabling fast decision-making on devices that operate in real-time environments. For instance, robotic vision systems can leverage pruned and quantized models to improve response times while maintaining the accuracy necessary for tasks like object manipulation or navigation. After applying pruning and quantization, fine-tuning is necessary to regain accuracy. Pruning removes weights, and quantization reduces precision, both of which can harm the model's generalization ability and accuracy. Fine-tuning helps to adjust the weights back to their optimal state, allowing the model to recover some of its lost performance. Fine-tuning typically involves retraining the model with a lower learning rate, allowing the remaining weights to adapt without drastically changing their values. This process helps the model adjust to the reduced complexity and lower precision without overfitting to the training data. It's a delicate balance between maintaining the model's efficiency while regaining as much of its original performance as possible. Looking to the future, we expect that adaptive pruning methods will become more sophisticated and tailored to the specific needs of different models and applications. We may see AI-specific hardware designed to optimize quantized and pruned models even further. The advent of quantum computing also holds the potential to revolutionize how we approach model efficiency. Quantum-based methods could offer new ways of handling large-scale models with more efficient resource management. Additionally, meta-learning could be used to develop more intelligent pruning and quantization strategies. By using meta-learning algorithms to optimize these techniques, we can automate the process and make them more efficient across a variety of domains. In conclusion, quantization and pruning are fundamental techniques for scaling AI applications, especially when deploying models in resource-constrained environments. They allow us to create smaller, faster, and more efficient models without sacrificing too much performance. The primary challenge, however, lies in striking the right balance between efficiency and accuracy. By reducing the model size and improving inference speed, both techniques play a crucial role in making AI more accessible, particularly in mobile applications, IoT devices, and edge computing. As AI systems continue to grow and evolve, these methods will remain central to enabling real-time decision-making and high-performance solutions across a variety of industries. Parallel and distributed training are essential techniques for accelerating the training process of large-scale models, such as large language models, LLMs, and making them feasible in a practical setting. These techniques allow the workload to be distributed across multiple computational resources, such as GPUs or TPUs, enabling faster training. The two main strategies are data parallelism and model parallelism. In data parallelism, the model is replicated across multiple devices, and each device works on a subset of the data. In model parallelism, the model itself is split across multiple devices, with each device handling a different part of the model's architecture. These methods help to optimize both the speed and efficiency of training, especially for models with large parameters or datasets. Data parallelism is a popular technique in parallel training where the model is replicated across multiple devices, e.g. GPUs. Each device processes a different batch of data independently, and the results are aggregated and averaged to update the model's parameters. During backpropagation, the gradients from each device are averaged to ensure that all copies of the model receive the same updates. This approach works well when the model itself is small enough to fit within a single device's memory. However, as the model grows in size, data parallelism can become inefficient, and other strategies like model parallelism may need to be considered. In model parallelism, the model architecture itself is split across multiple devices. Each device is responsible for computing a different part of the model. This is particularly useful when the model is too large to fit into the memory of a single device, like in the case of deep neural networks, DNNs, or transformer models. While model parallelism allows us to scale larger models, it comes with a challenge: increased communication overhead. Since different devices are responsible for different parts of the model, there needs to be continuous communication to pass intermediate results between devices, which can slow down training. Therefore, balancing model partitioning and minimizing communication time becomes crucial. Hybrid parallelism is a combination of data parallelism and model parallelism. This approach is particularly useful for very large models that don't fit within the memory of a single device. In hybrid parallelism, the model is divided into smaller parts, and each part is placed on different devices while multiple copies of the model process different subsets of the data. This allows us to scale efficiently across a large number of devices and helps mitigate the communication bottleneck that arises from using only model parallelism. By combining both strategies, hybrid parallelism provides the flexibility to handle large datasets and large model architectures simultaneously. It's an effective solution when the model is too large for a single device, but still needs to be trained in a parallel fashion. In parallel and distributed training, we need to decide whether to use synchronous or asynchronous updates for gradient synchronization. Synchronous updates require that all devices finish processing their data and calculating gradients before updating the model parameters. This ensures that the updates are uniform and accurate, but it introduces latency because all devices need to wait for each other. Asynchronous updates, on the other hand, allow devices to update the model parameters as soon as they finish processing their data without waiting for the other devices. While this can speed up training and reduce idle times, it may lead to less stable updates, as the model might be updated with inconsistent gradients. Each approach has its advantages and trade-offs. Synchronous updates are typically more stable, but asynchronous updates can often speed up the training process. Multi-node training involves spreading the training process across multiple machines, or nodes, where each machine can run a separate process or device. This is often necessary for very large-scale training tasks, such as when training large language models, LLMs, or complex image models. A popular framework for multi-node training is Horovod, which facilitates distributed deep learning using data parallelism across multiple nodes. Horovod allows for efficient scaling across machines and can work in tandem with frameworks like TensorFlow and PyTorch. Multi-node training enables the use of high-performance computing clusters to scale training workloads, significantly reducing the time needed for large-scale model training. However, this method requires careful management of data partitioning, synchronization, and fault tolerance. When scaling model parallelism across multiple nodes, parts of the model are distributed across different machines, each of which is responsible for computing a subset of the model. This allows for training very large models that would otherwise exceed the memory capacity of a single machine. However, distributing the model over multiple nodes comes with its own challenges. Communication overhead becomes a significant factor. as each node needs to exchange intermediate results and gradients with the others. Efficiently managing this communication is critical for ensuring that the multi-node training process doesn't become a bottleneck. Pipeline parallelism is a technique where the model is divided into sequential stages, with each stage assigned to a separate device. This allows each device to work on a different part of the input data, with the output of one stage serving as the input to the next. By using pipeline parallelism, we can achieve better resource utilization as multiple stages of the model can be processed concurrently. However, a potential downside is the risk of stalls, which occur if the stages are not properly balanced. For instance, if one stage is slower than the others, it can delay the entire pipeline, reducing efficiency. Optimizing pipeline parallelism requires careful planning of stage division and balancing workloads. Mixed precision training involves using a combination of 16-bit and 32-bit floating point precision during training. The idea is to perform most of the calculations using lower precision 16-bit numbers, which reduces memory usage and increases throughput, while keeping critical operations such as weight updates in 32-bit precision to maintain numerical stability. Mixed precision training is particularly beneficial in distributed training environments, as it improves the scalability of models on GPUs and TPUs by reducing the memory footprint, allowing larger models to be trained in parallel across multiple devices. It's an effective way to speed up training without significantly sacrificing model accuracy. Parallel and distributed training offer great benefits in terms of scaling, but they come with several challenges that need to be carefully managed. One of the main hurdles is the synchronization overhead. In a distributed setup, multiple devices work concurrently, but the model updates must be synchronized at regular intervals. This process can introduce delays, as all devices must wait for each other to finish before updating the model. The more devices there are, the more significant this overhead becomes, potentially leading to bottlenecks. Another critical challenge is managing the communication between devices. Each device needs to exchange information, such as gradients during backpropagation, which can become time-consuming, especially when large amounts of data are involved. If the network bandwidth is insufficient or inefficiently utilized, the training process will be slowed down. Additionally, fault tolerance is essential in a distributed setting. If one of the devices or nodes fails during training, it can disrupt the entire process. Thus, building systems with high reliability and mechanisms to recover from failures is important. This often involves saving checkpoint data and employing replication strategies to avoid data loss. Finally, ensuring load balancing across devices is another challenge. If one device gets overloaded with too much data or computation while others remain underutilized, it can result in inefficient training. Balancing the load optimally across all available devices is critical for maximizing performance and resource usage. Scalability is a key benefit of parallel and distributed training. The ability to scale a model across multiple devices is essential when training large-scale models. However, the degree of scalability depends on several factors. The number of devices you have is a primary factor, but it's not just about adding more machines. The performance of the network linking these devices also plays a critical role in scaling. If the communication between devices is too slow, it can negate the benefits of adding more hardware. Using frameworks like PyTorch Distributed can help in managing scalability. These tools are specifically designed to handle distributed deep learning tasks, offering optimizations like efficient gradient synchronization and fault tolerance mechanisms. Another crucial factor that affects scalability is the size of the model and data. Moreover, handling communication bottlenecks is key. If the communication between nodes is not optimized, it could slow down the entire training process. Efficient parallel training requires algorithms that can manage large models and datasets while minimizing the time spent on communication and synchronization. Ring-all-reduce is one such method commonly used in distributed training to synchronize gradients. Rather than broadcasting gradients to all devices at once, ring-all-reduce minimizes the amount of data transferred between devices by arranging devices in a ring and allowing each device to send and receive data in a circular fashion. Another strategy is the parameter server, which allows for efficient management of model parameters across a distributed system. By centralizing the model parameters in a parameter server, workers can asynchronously update and retrieve parameters, making it easier to scale to large datasets without causing synchronization delays. Finally, lazy updates can be used to reduce the frequency of communication between devices. In this approach, devices do not send updates immediately after processing every batch of data. Instead, they only synchronize after a specified number of updates, thus reducing the communication overhead and potentially speeding up training. Fault tolerance is a fundamental aspect of distributed training systems. In a multi-node environment, a failure in one node can halt the entire training process, leading to significant disruptions. To mitigate this risk, distributed training systems need to have mechanisms for ensuring reliability and continuity. One common fault tolerance strategy is checkpointing. This involves saving the current state of the model, such as its weights and gradients, at regular intervals. If a failure occurs, the system can resume from the last checkpoint rather than starting over from scratch, saving significant time. Another approach is replication, where copies of the model or key data are stored across multiple devices or nodes. This ensures that even if one node fails, a backup copy is available to continue the training process with minimal disruption. While fault tolerance is essential for maintaining training stability, it can add to the overall training time due to the overhead of saving and recovering data. To ensure distributed training is efficient, it's important to optimize various aspects of the system. One of the best approaches for large models is to use hybrid parallelism, which combines both data parallelism and model parallelism. This enables the workload to be distributed more efficiently across multiple devices. Optimizing communication patterns is another crucial factor. By minimizing the amount of data exchanged between devices and reducing communication frequency, we can significantly reduce training time. In addition, using adaptive learning rates can improve the convergence of the model by dynamically adjusting the learning rate based on training progress. This can result in faster convergence and better accuracy. Lastly, memory optimizations such as gradient checkpointing or mixed precision training can help reduce memory consumption, enabling the training of larger models on limited hardware resources. In conclusion, parallel and distributed training are powerful techniques for accelerating the training of large and complex models. By distributing the workload across multiple devices or nodes, these methods allow for faster processing and reduced training time, making it feasible to train massive models like LLMs. The main strategies for distributed training include data parallelism, model parallelism, and hybrid parallelism, each of which has its strengths and trade-offs depending on the model and hardware. The efficiency of these methods depends largely on the ability to manage scalability and communication overhead. Additionally, fault tolerance is a crucial aspect of distributed training, ensuring that the process remains robust in the face of hardware failures. By implementing techniques like checkpointing and replication, we can safeguard against data loss and maintain training stability. Thanks for watching! This concludes our day 9 of the course. For more AI courses and interview materials, please visit bowz8.com.